SwayamPrabha. Digital India. Educated India.
Okay, so in the last class we have been talking about multiple Hopf bifurcation that we predicted by plotting equilibrium amplitude versus Reynolds number, and if we do present our direct numerical simulation results, what we notice there are visual kinks. So these are the locations where it would appear that various bifurcation sequences have merged. For example, this could be the coalescence point of the first bifurcation and the second bifurcation, right. So essentially we are not completely throwing away the Landau model itself. All that we are saying, to use the same equation, we need to actually explain it in terms of multiple bifurcations, right. So this is what we wanted to do, and then what we talked about, that we could perhaps try to fit it with a sort of a parameter in terms of epsilon. Epsilon is nothing but the departure of the local Reynolds number from the critical Reynolds number, and if it was truly parabolic, then what should have happened? We should have had only the k1 term, right. This other 3 terms should not be there. But let us see what happens when we do it like this, so that the A square is given in terms of that quartic, and then we have the data on those 3 segments. What we do is try to feed this coefficients k1, k2, k3, k4, and then we see what happens. So we have basically 3 ranges of Reynolds number, starting from let us say about 52 to 80, then 80 to 133 and 133 to 250. K1 is in the range of 10 to the power minus 4, right, whereas K2 is in the range of 10 to the power like minus 5 or minus 6, depends on which range you are looking at, and these are much lower in value. For example, this goes as 10 to the power minus 6, and while this one is even smaller by 1 order of magnitude. So ideally what you can see is a predominant dependence on k1 and lesser dependence on this. So this kind of tells us that even this kind of empirical fit will lead you to that same kind of Landau model. Okay. So this is in a sense that what we get. We can get those 3 sets of values merging onto the 3 points of Hopf bifurcation, and in this we have also put in a correlation which was produced by Norberg. Norberg actually used a set of experimental results for his, I think, PhD thesis work in a wind tunnel, which was characterized by a turbulent intensity of about 0.06%. And based on his experiments, he produced this kind of empirical fit. So these are not truly experimental data, but it is a kind of a empirical correlation, and that kind of gives you a value which is close to 49 or so. Okay. So this is the kind of thing that we would see. So now what I would like to do is move over to find out what the role of this background disturbance is going to be. So what is the background disturbance that we can think of in a, let us say, in a wind tunnel, that would be the free stream turbulence, right. So, we state very clearly that if we are looking at real flows, we will have this always present free stream turbulence. It could have a low amplitude of excitation, but that may be good enough to alter the bifurcation sequence, right. Free stream turbulence, by definition, actually people have tried to view it as a random event, and people do try to view it and model it stochastically. One of the most popular way by which people in computing have used it is treat it as some kind of a random number, and then impose that random disturbance to your to the inflow path of your flow. We have actually departed from that point of view, that free stream turbulence has a definitive origin. And what is that origin? If you understand how we design experimental devices, you would know where the free stream turbulence is coming. What is it that you are trying to do? You are trying to mimic the actual flow, where maybe the body would move in a quiescent flow, or what we are talking about, a quiescent flow, it need not necessarily be quiescent. There could be still some kind of a convection of vertical disturbances, right. Whatever that is, in the wind tunnel, what we do, we keep the model, the body fixed, and create a flow. And how do we create a flow? We create a flow by having some kind of a air screw, right. We have some kind of a circulatory device, and that creates a flow which converts it into a rectilinear flow. Now, in the process, what happens? Since the flow has begun with some kind of a circulatory motion, the remnant of that circulation is there. In designing wind tunnel, what we try to do is, we try to break down this larger vortices into smaller ones, and that is what you see. You have all those honeycombs and screens doing it for you. So, basically what we are talking about in terms of background disturbance, what we call are those remnants of those large eddies, which are originated in the size of the propeller that is driving the airstream. But through the action of the screen and honeycomb, we break it down into smaller ones. So, that is what we get as free stream turbulence. So, having obtained that point of view, we try to really model the FST, and we understand that different tunnel will have a different design. So, you will have a different FST environment. For that matter, talk about the same tunnel. If I try to run the experiment at different speed, then what is happening? I am rotating my fan at a different RPM, and that is why the FST is going to be different. This is something people did not quite appreciate, but we did say that we need to view FST as a combination of two components. One is kind of a deterministic component that comes from the fan size and its speed, so on and so forth. In addition, when we have this smaller eddies being created by the action of this honeycombs and the screens and the contraction sections, which all modulate them, that gives you some kind of a statistical appearance, which people have been talking about. So, let us now look at what we can do. In modeling the free stream turbulence, we note that the statistical description of the turbulence gives us various moments, right? The various moments. One of the most common moment that we usually use is, let us say I am trying to create u infinity. So, in the tunnel, what we end up doing is some kind of u prime, v prime, w prime, right? And where this u prime, v prime, w prime are those random stochastic component. Then I could define the variance What about the mean? Mean is straightforward. These are truly random quantities, the mean will come out as u infinity. The variance goes as given by this turbulent intensity that we talk about, which is nothing but u infinity square v infinity square plus w infinity square divided by 3, and then I will take a square root of that. I will non-dimensionalize with respect to u infinity. So, that is what we are saying. So, this is what? This is a second order statistics. Okay. And this is what you will find in the literature all the time. People talk about this as if this single number characterizes the tunnel. But as I explained to you, the same tunnel working at different speed will give you different value of Tu. So, it is quite a misnomer to characterize a tunnel by a single number like Tu. Now, what happens to the other statistics? We can talk about the third order statistics, which is called the skewness. If the statistics was truly a combination of infinite number of sources, they would have all worked independently. Then through central limit theorem, we would have seen this probability distribution function of these variations would have been like a pure bell curve, like Gaussian, perfectly symmetric. However, it does not remain so. As I told you, there is a distinct bias because of the design of the tunnel. So, that is what the skewness basically represents. The skewness represents a deviation from the symmetric distribution. So, my PDF is not symmetric, it is asymmetric, and that is this given by the skewness. So, this is your third order statistics, and it has been actually shown long ago by Batchelor and Townsend that even if you are looking at say homogeneous turbulence as it is created in an experimental scenario, this skewness is contributed by the instability of the flow, right. So, there is this seed of instability that is there in the skewness itself. Okay. And if I create a kind of a very well designed tunnel, then I would have a u infinity here, and then the variance etcetera would be such, all the moments would be such that I actually would like to get it like this, a perfectly symmetric distribution like this. But as I told you, it will not be symmetric, and there would be one more factor, that we are saying it is going to be band limited to a small number, and then it becomes 0 and remains so, but that is not what you get. What you are going to get is some kind of a tail at the high frequency. That is given by the fourth order statistics or kurtosis. Okay. This is what is called as the flatness of the tail of the distribution. So, we need to really worry about all this. So, while skewness gives you some kind of an instability, the kurtosis tells you what happens at high wave numbers, high frequencies. Kurtosis tells you about that, right. So, you know, computer generated random number cannot be a true substitute for free stream turbulence. This is what we did realize, and we did model it. And in experiments, as I told you, there are low frequency deterministic sources because of the way the fan is positioned, because of the way the honeycomb, the screens are. That creates a kind of a deterministic source. So, if I am trying to model, develop a model of turbulence with respect to some experimental data I am trying to simulate, then I must introduce that deterministic source, right. This is what we need to do. So, what happened is we did some measurements in one of our smaller tunnel, and then we developed a free stream turbulence model. And what did we do? We wrote down I think let me see, yeah, we wrote down one of the disturbance component given like this. Okay. It has some kind of a normal distribution. So, what happens? The random number that you generate in computer, they are basically uniformly distributed from -1 to +1. So, from that uniform distribution, you can convert it into a normal distribution. What is a normal distribution? It is a kind of a Gaussian. So, it has a 0 mean, and you have some second order moment. So, what you do is you generate a time series that is given in terms of the normal distribution at time t and the prior time t minus 1, okay, and this is multiplied by some coefficient alpha that we want to keep it, because we are going to mimic the second order moment and the fourth order moment, because these are constituted by normal distribution, a combination of the two will always give you some kind of a even moments only. So, with the help of that, so we could fix the second order statistics and the fourth order statistics, and the deterministic event of the tunnel itself would be explicitly kept. That corresponds to basically the skewness. So, that was the whole idea of generating this particular turbulence model. So, what happens is we could do that, and that is the story of this particular FST model that we developed. And what happened is, because we pick up the low frequency event from the tunnel empty tunnel data itself, it of course matches quite well at the low frequencies, low wave numbers. In addition to that, we fixed the constant alpha to match the second and fourth order statistics. And this is the model that we have created, and we have computed this flow field using that. Okay. And this is how it looks like. So, if I go to the tunnel, measure the free stream turbulence, this is how it is going to look like. So, this is your experimental FST data, and this is what we synthesize. So, this is your synthetic free stream turbulence. And now, you see what happens, we use such a free stream turbulence model, okay, and then see what we get. So, what we did, we took the value of FST as given by this Tu, which is given by 0.06%, exactly the value that Norberg quoted. And then you see what happened is the calculations without the FST goes like this and meets there around 53.2907. The moment we switch on an FST model with 0.06% Tu, we go and get a value of 49. So, you can see this is what actually people should be doing, and we have successfully demonstrated here that indeed the background disturbances can create a Hopf bifurcation onset at an earlier Reynolds number. Okay. So, this we talked about how we go doing it. Only thing that I did not mention, that the c is the propagation speed of all those eddies coming with it. We did some exercise and we figured out that if we keep it below u infinity, it is good enough. It is quite insensitive to exact value of c. So, you can just give a sort of a value of c which is less than u infinity, and that should be all right. So, in a sense, what we are doing is the following, that if I have a cylinder, and then this is what we compute in a large domain like this, and then what we do is we identify a region where we call this as the inflow, and this is what we call as the outflow. And in the inflow, what we are doing, unlike what everybody else does, we get u infinity, and u prime, b prime. If we are doing a 2D calculation, we will only have two components, u prime and v prime. That is what we put in there. Okay. Well, if you have done a pretty good tunnel design and the contraction is not too rapid, then it is quite okay to consider that u prime and v prime have the same statistics, right, kind of isotropy you can talk about. But if you want to also include some additional information you may have, like for example, in a channel flow, you know v prime is going to be less than u prime, and then you can put it in there, and you can actually get also this nice wall normal structure that we can put it. There are experiments available. So, we can do that. That is what we are saying, that in solving the Navier-Stokes equation, we try to solve it in terms of the stream function vorticity equation. So, this is your stream function equation, and the vorticity transport equation is this. Okay. So, when we are trying to solve this vorticity transport equation, at every time step we are going to add this u prime and v prime, and this u prime and v prime you are going to run your FST model at every time step for each of the points. So, that equation that I shown you before in terms of E t and E t minus 1. So, in all the points here on the inflow, we run the code subroutine and generate u prime v prime, add it, and we can keep doing it for all the points. Okay. And we did compute that case that we showed you there with the help of this kind of model. Okay. Okay, so why should noise be important? Why should noise be important despite what we saw in Landau's equation? While talking about the Landau's equation, we commented what? That long term solution is independent of the initial condition, right. We eventually get into AE, right, and that AE, what we found, comes out like this. So, what happens? We have the flow in the following sequence, that we have an onset of linear instability that non-linearly saturates and gives you this. But if we are talking about the linear instability, we know linear instability has the receptivity aspect. That is what we have talked about. So, that is the reason that we must have strong dependence of input disturbance, the way we are going to get the instability itself, because that is how it begins, right. So, for every Reynolds number, this quantity itself, sigma r, depends on the background disturbance. So, that is why we should have that. Now, that was also the reason that Hohmann could do that. Hohmann's experiment was one such brilliant experiment, where this control of primary instability was achieved by the working medium itself, because it was very highly viscous fluid, and it could dissipate those background disturbances, and you could sort of delay the primary instability indefinitely. Now, I think we now have a fairly decent idea of what happens to blob body flows, right. So, there is not much. Now, we need to know a little more about it, and what we need to know more about it is achieved by using the computed results. Now, we have the ability to compute the flow with and without disturbance, and then we can sort of post process the data. And what do we do by post processing? That is where we use a technique called proper orthogonal decomposition technique, which was pioneered by Kosambi, and which has been later on sort of very much popularized by Professor John Lumley and his group, and that is related to the stochastic fluid mechanics, specifically in understanding turbulent flow, and that is given in that monograph of Holmes, Lumley and Barkous. So, you must be aware of this reference, Holmes, Lumley and Barkous. This is a monograph, I think it was printed in 1996 by Cambridge University Press, one of the brilliant book. See, Kosambi was a mathematician. His idea was very simple, that this debate is going on whether this physical world is deterministic or random or whatnot. So, he said, like in many dynamical systems, when you look at the response field, it may look stochastic, chaotic, but then underlying that stochasticity, there might be some deterministic structure involved. He was so far ahead of his time to think of it not necessarily with respect to turbulence, but he was talking about a general dynamical system. So, he said that can I take this stochastic system and project it on a deterministic basis. What will be the property of this deterministic basis? They will be kind of a linearly independent. So, they are going to be orthogonal to each other. So, it is like taking your orthogonal functions. A very simple example is your trigonometric functions, like the Fourier transform that we have already seen, that I could take sine and cosine. So, each one of them are going to be orthogonal to each other. So, that is what is being attempted. So, that is what he was trying to understand, that even when you are looking at complex stochastic system where the dynamics is given by space time variation, you can actually project the whole thing in terms of a deterministic basis. So, where do you start and where do you get off? That is a major question. That question also he answered, that for example, if I am looking at, let us say, a mechanical system like a fluid dynamical system, I will go on taking this orthogonal functions up to a level which more or less defines the major events of the flow. So, in a fluid flow, it could be, let us say, the energy. If I can decide, say, explain 98% or 99% of the energy, I am done, right. So, that was the whole idea behind what Kosambi started, and which was brilliantly exploited by Lumley and his colleagues. Now, POD as a technique was further given a boost by Cyrowicz. Cyrowicz said, look, how do I do this decomposition? It's like basically it is a continuous system, right. So, if I look at the continuous system, then what I could do? I could take a snapshot and I have all these points, and then I can decompose it, the corresponding sort of a discrete description, I can define it, because eventually what you do when you actually compute, you end up solving some A x equal to b equation. The dimension of A determines your discretization, but this discretization theoretically speaking should have been infinite dimension, because it is a continuous system. But what we are doing in computing, we are discretizing and making it a finite number. But even that finiteness in a computational sense can become very bothersome. So, that was one way of doing it, and we did look at one such way, that if we look at the spatial discretization and then try to find out the eigenvalues and eigenvectors of the spatial discretization by a iterative process due to Langevin. That is one way of doing it. You get a pretty good picture. In fact, the picture that you get, we found out a very interesting property, that if I take a large domain and I do it in two small parts, and I get the picture and I then put them side by side, they just match seamlessly. So, what is it that we are doing? If I have say n by n dimension picture, and if I do n by 2 and n by 2 dimension, I just make it into say 2 parts, then what happens? Your corresponding A matrix dimension has come down, and in terms of solution process, the computing goes as n, the matrix to the order 3. So, if I can subdivide the domain into smaller domains, and I can compute them separately and put the picture together, I get a full picture. So, that was something that was attempted, and it was quite okay, but still it amounted to lots and lots of work. However, much earlier, Lawrence Aerovitch, he did propose an alternative way of doing it. He said, don't look at the picture in terms of space, but look at in terms of time. So, what you do, you grab lots of snapshots at different time intervals, and from that information, because you are anyway what you are trying to project, you are trying to project a spatiotemporal event. So, you try to get the picture by looking at snapshots at different time and reconstruct the average picture over that time interval. So, the basic idea is what? It is a stochastic system. So, we are trying to give it some kind of, in the decided time horizon, get a kind of a fit of this space time variation by a deterministic picture, subject to the constraint that this explains 90% of the energy, or this explains 95% of the energy. So, method of snapshots is so much more beneficial, because instead of talking about, let us say, millions of points, here we are going to talk about fewer snapshots, number of pictures in time. How many that could be? Like Yogesh will tell you that you take an interval of, let us say, delta t of the order of 0.01. So, in a unit interval you take 100 pictures, and then of course, sooner or later you reach the limit of your processor and you stop there. But still, that is much better than what we have before. We will talk about little more in detail about method of snapshots and how to interpret the data, but this was a sort of a remarkable achievement by which this whole subject of POD technique got a boost, and it was revived. That is all due to Aerovitch. Okay. So, in many fluid dynamical system, it is not necessarily have to be one of turbulent flow. Any unsteady flow, we can make use of it, and in fact that is what we are trying to do now, because we are going to use this POD technique to study instability of flow, and during instability we have already seen that it is going to be a space time dependent phenomena. So, can we use POD for studying instability? That was the question that we been asking for last few years. And I think we have now come to a state where we have been able to develop a very coherent picture of it, and we'll see some of these results. Okay. So, if I am going to look at the dynamics of a system where stochastic component is not very important, like flow instability we are talking about. So, there are no such stochastic components involved. Then what happens? With the help of the POD, we can develop a physical model of the dynamical system. So, that is what we have been attempting, and in this method what we are doing, we are taking a number of snapshots, let us say m of them, and we use it for the analysis, and this really is a very easily done. So, what happens is, first and foremost, of course, you will have to get results which are meaningful. One of the reasons that POD had a little stuttered start is for two reasons. If you try to use it with experimental results, you are very much affected by the experimental results accuracy. So, that has not been done very well. And we also have not started talking about turbulence, which we will be doing shortly. Then you will realize that when we talk about turbulence, turbulence is an end product after the instabilities have taken over. So, you may have some kind of a sort of a saturated state, which is not very sensitively dependent on the fluctuation of these parameters of the system. Whereas, when I am looking at the stability of the system, you now know very clearly that the disturbances are very important. So, if I am going to use POD for unstable flow, that is going to be much more demanding than using POD for turbulent flow. This is something we have to appreciate that. So, when we are trying to use POD to study instability, then we better have what we call as a direct numerical simulation. So, where we would be getting the solution without making much of error, right. So, what really happens is, we perform DNS, then we collect a set of snapshots which we call as the ensemble, and then taking this reduced number of snapshots, we come out with basis functions which are directly related to the number of the snapshots, right. So, that is what we are doing, and this gives you a kind of a mathematical modes which give you a very good representation of the dynamics of the system. So, what we are going to do now to perform this POD analysis, we will choose a time horizon over which we will get some kind of a mean or the equilibrium flow, right. So, what we do is, if I choose say from T1 to T2, I take a kind of a time mean, and then once I have it, and I also through the DNS I am going to have an instantaneous realization. So, I can subtract one from the other, then I can get so called disturbance flow, and on this disturbance flow I can embed the POD technique. Then I will see how these disturbances are growing. You see, that is how we have approached the study of stability in various forms, and what is very satisfying in this approach is you are doing it with the full nonlinear equation without any empiricism, without any restrictive assumption. So, instability analysis based on POD will be a much more complete description of the system than anything. So, if I use velocity field to define the disturbances, then what we are going to get? We are going to get an estimate of the kinetic energy. And if we are going to use vorticity as the disturbance field, then what we get is called the entropy. So, we can talk about If I am using velocity, I get kinetic energy, and if I use vorticity, I will get what I call as entropy. Okay. So, we basically prefer working with the vorticity field, because that is what fluid mechanics is all about. It is all about vorticity dynamics. So, you work with vorticity, you work with entropy, and that is how we are going to do it. And I am just going to stop here by showing you this result. We have done this simulation of flow past a cylinder at 3 different Reynolds number, 250, 100 and 60. I am going to describe it, but you can see a very curious feature, that this is more colorful than this. Okay? I will stop here, we will begin from there in the next class, that is tomorrow.